something as simple as a bicycle can change in has about 6 or 7 degrees of freedom. The rotation of the handling of the main bar, right? Each one of the wheels can rotate on its own, that's 3. The pedals can also rotate on their own, that's 4. The bicycle can move, that's 5. And I can't think right now of the 6th one, but maybe it has to do with the gears that tie the pedals to the back wheel, that's 6. 6 degrees of freedom. A bicycle would need a 6-dimensional space to represent all its possibilities. But let's stay away from bicycles for a second and stick to the simpler ones. The human body, depending on what aspects of the human body you concentrate on, has 1,000 or more degrees of freedom. So you would need a 1,000-dimensional phase space to capture the physiological changes of the human body, the anatomical changes of the human body, the behavioral changes of the human body, the mental changes of the human body. It's not 1,000, perhaps an infinite number of degrees of freedom. Henri Poincaré can handle objects with an infinite number of degrees of freedom. In other words, he gave us all the mathematics to handle spaces with as many degrees of freedom as you wanted. The more degrees of freedom, the harder they become to study, but nevertheless, he can handle it. Right? We're not going to go into that because I'm going to stick to two-dimensional spaces, right? Just for the sake of making things clear. Now, after you do that, and let me draw my little space here. And I always draw this bent piece of paper, even though actually the spaces are very different. They cannot have edges, because then what happens when the trajectory leaves the edge? But let's forget about that for a second. You assign speed to each one of the two dimensions, one of the degrees of freedom. So that's one. Speed is another one. That's position. And now every point in that space becomes one possible state for the pendulum, one possible state for the object you're studying. Since the pendulum can be fully characterized at any one point during its dynamics by where it is, by its position, and how fast it is going, it can be fully characterized just by giving where it is and at what position it is going, you know the present state of the pendulum perfectly accurately. So that means that every point in the space becomes one possible combination of speeds and positions, becomes one possible state for the pendulum. By doing this, by creating phase space, we have managed to represent visually all the possibilities available to the pendulum. This was easy because we had an object with very few possibilities. It becomes much more complex and much more dramatic when you have something like an animal or a plant, which has many more possibilities. But nevertheless, the present time, the present state, at any one point in its dynamics will become just a single point in that space, which means that all the possibilities for the pendulum are in that space. Yeah?
Why is that on an XYZ axis? Shouldn't it be, there's just two variables? Should it not be X and Y?
Where is X and Y, I'm sorry?
Well, she would say that speed would be Y, for example.
Oh, no, but X and Y only exist if you add those coordinates. To get X and Y and Z, you need to have a fixed set of coordinates because it's relative, every point relative to the distance, to that reference set of coordinates gets an X, Y, and Z. Once you eliminate that, there's no X, Y, and Z. Right?
Okay.
Each one of these points, in fact, as I said, since now you don't have any way of using a reference to identify it, you simply identify it by the rapidity or slowness with which curvature is changing at that point. Remember, I introduced that in the first class, but maybe I forgot to say it again. Yeah?
In the case of a pendulum, is every swing that it does unique?
Well, in the case of the pendulum, being such a constrained system that is always attached to its bit and doesn't change weight.
That's always the same thing, but Is every swing?
No, the swings actually become, if I drop it from here, the first swing would be the widest, the next swing would be a little less wide, next swing a little smaller, and until it comes to rest here. In order to keep the pendulum going, click, clock, like in a grandfather's clock, you need to attach it to a little motor, something that's giving it a push. That's why clocks can keep their pendulums going. But a regular pendulum without a motor, if I let it go from up here, it will swing wildly first, but then the swings will get more and more mild until it comes to a rest.
In terms of intensity of the procedure, yes, but does that mean that every degree of freedom, manifests in one thing?
Or the
It
coin
can
is
do
always the
every degree
same.
of freedom is one thing, one move. Is one
Well, every degree of freedom is, again, in particular, we're talking about such an object that can become it can only change in position, it can only change in speed, that it's really a boring object. Let's not try to use this to try to imagine the degrees of freedom of, I don't know, clouds or hurricanes or mountains or plants, which are much more elaborate, much more numerous. I'm starting with a very simple one because it's the best way of getting to the point. But you can create space of very, very complicated objects. Right now, I'm sticking to the simple one, right? Now, at any point, any present position of the pendulum can be a point, which means that a sequence of states of the pendulum can become a line. They become a line in this point. In particular, if we create an entire, I'm going to take the pendulum up here, and I'm going to put it here. Let's say that this was speed 0, and this is position 0. So I'm going to take it here, I'm going to let it go, little by little. The next position that it has when the pendulum is here, it will be here. The next position it has when the pendulum is down here will be here. And so now I draw all the different points. This is how the pendulum would look until it comes to speed equals 0, position equals 0. In other words, a swinging pendulum leaves this pattern in phase space. A spiral that has a big swing, a smaller swing, a yet smaller swing, a yet smaller swing, until it comes to rest. Yeah? What Poincaré was giving us is a way of visualizing something dynamic. In this case, it doesn't save you that much because you might as well look at the pendulum. But once you start going into 3 degrees of freedom, 4 degrees of freedom, and something can change in temperature, pressure, position, and speed, your eyes cannot really follow all the becomings, but in phase space, they will still be just trajectories that do a certain motion and do a certain thing. Yeah.
How does this relate to quantum mechanics and
Well, in quantum mechanics, they use a special type of phase space called Hilbert space, that it has an infinite number of dimensions, so that it is like incredibly complex, and that is where they plot all the possibilities of positions of the electron, all the possibilities of position of the nucleus, and when you have 2 atoms smashing themselves against one another, the result of those 2 atoms, you can also plot them in Hilbert space. To be quite honest, my degree of, my ability with mathematics doesn't get to the point to understand Hilbert space, but the idea being that in quantum mechanics, they just simply borrowed Poincaré's idea. Poincaré's idea has been borrowed by everybody. Today, every biologist, every chemist, every physicist creates phase spaces as a way of trying to get intuitions as to what happens to a particular system. Now, this is the basic ideas. Let me start now going into the slightly more elaborate things. So Poincaré invents his space. He's starting to play with it. This is 1902, 1903. He starts changing things around. I'm going to again draw the same